Hello. Hi Anuji, how are you? I'm also good. Okay. Yes, yes. Hello, good morning, everybody. I'm Karan Bal from 3D Fusion, and we are a company in Noida, and we do all the 3D printing stuff. So basically, we do 3D printing as a service. We also manufacture 3D printers, and we do all sorts of design stuff and CAD services, all those things. So today we will be presenting about the overview of 3D printing and what the ecosystem is all about and what all are the specifics of different technologies used within the 3D printing and also the applications where we can use 3D printing and it is being used right now. So let us start now. Okay, so what is 3D printing? Basically, like 2D printing, in which you print an image on a piece of paper. So that ink that got printed on the paper has some sort of thickness. So consider that as one layer. So, but in 3D printing, there are multiple layers. So one layer on top of another that makes the 2D printing thing. So first of all, the basic challenge which comes to the engineers is to design a part in such a way that it is manufacturable with some kind of manufacturing process. Okay, so sometimes the designers use injection molding as a process. Sometimes they use, basically there are two three types of processes in the manufacturing space. So first is the formative process. So formative processes are like injection molding, casting, and stamping, forging, all those processes. So formative manufacturing typically forms material into the desired shape via heat or pressure. So like in injection molding, there is a mold and we inject molten liquid the molten liquid plastic into the mold and then cool it down and the liquid turns into the shape of the mold, so you have the final product. So similarly in casting also, there is a sand casting, various kinds of casting. So in casting what happens, the molten metal is poured into the cavity of the mold and the process completes the manufacturing thing. So the designer, when designing the part, has to take care of all those parameters because every manufacturing process has its own limitations. Some parts will not be able to be manufactured if it is not optimized in a way to be manufactured in that process. So basically the formative process in which we use heat and pressure to mold our parts, it can be metal, it can be plastic. The second kind of basic manufacturing process is subtractive. So in subtractive manufacturing, what happens is there is a solid block of material that you take and you selectively subtract the material from that block and you will get the final part. So it utilizes cutting tools like CNC, lathe, turning, and drilling. Those operations are subtractive operations. So the subtractive manufacturing is capable of producing highly accurate parts. The surface finish is very good, but the cost for per part is very high for those kind of processes. So and there are limitations to what we can achieve with the subtractive. So the third thing to counter the limitations of the subtractive and formative processes, we have the additive manufacturing, which is the 3D printing basically. So in additive manufacturing, the process is basically there is nothing right now. We don't have to subtract anything from the material. We start laying the layers one on top of another to make the part. So as in subtractive, there is a block of material and we are removing the part. So that's why it is called subtractive. But in additive, there is nothing. We just put on the layers one on top of each other. So, okay. So what is 3D printing? Basically, I have just told you, it's just like a printer. If you are printing an image on a piece of paper, so that image has very small thickness. So if we lay the same thickness on top of each other many times, then you will get a 3D physical object. So in the case of the printer, it will be in the form of a ink, but now rather than using the ink, our raw material in 3D printing is plastic material. So it can be of solid or liquid nature depending on what technology we are using in the 3D printing. But basically, this is what the printing is 3D printing is all about in the basic sense. So, like in a normal 2D printer, we have digital image, the image in your JPG format or whatever image format, and then we turn it into a physical 2D image. So, similarly, we have a 3D image file which is called CAD file basically. So, there is a format which is called STL format. So we have the STL format as the starting point, and then we print that STL file, the 3D STL file, into a physical part. So how this 3D printing got started? So this technology was developed by Charles Hull in 1984 by 3D Systems. So that time it was called stereolithography. So it is a subset of 3D printing nowadays because it is just one technology of 3D printing that is being used even today. There are others also, and even far better and far economical than this stereolithography. But this was how it started. Then after in 1990 something, 1995 or something, the Stratasys came up with the FDM system, which was using the so this stereolithography uses a liquid raw material, and the other one uses the solid raw material. I'll tell you about these in following slides, so don't get confused. If you have any questions, you can ask at the end of the session. Just give me. Liquid raw material. Okay. So so yeah, so in 1993, MIT also had a kind of similar technology in which they were using inkjet printers to lay the layer on like droplets on the base, and then it is used to cure using the UV light, and then another layer comes on. So these were the initial technologies for the 3D printing. So now let's come again to the conventional processes. So first one is the injection molding. So injection molding is basically, as I told you, there is a mold. So this is the mold. If you can see my pointer, so I'm pointing to the left side of the left image. So these gray things are the mold cavities. So this is basically a negative space of what you have to make. So in this cavity, there is a nozzle on the top, and it pushes molten material into the mold, and it takes the shape of the cavity. Then this mold cools down, and the mold pieces are switched apart so that the part can exit. So this is the injection molding. These are conventional things. The cost per part of this is very low if you have a very high volume, like you have to make 20,000, 30,000 parts. So at that point of time, the feasibility and the economics of the injection molding process will be most suitable for the user. But the cost for making the mold is very high. So it goes into lakhs of rupees, even for a small, let's suppose you can say a bottle like you are seeing in this video. So even a mold of a bottle is like more than 4 or 5 lakh rupees. So, but if you want to make one part, then or a small batch, then the injection molding process will be too high cost for you. And also, you cannot change any design. For first part you're making the mold, then if you think you have to change the design a little bit, you will have to make the whole new mold. So for iterative designs and in the development process, the injection molding is not very suitable. It is basically for the volume run, like wherever you need thousands of and your design is finalized. So then we go to injection molding thing, because the per part cost is very less. So then comes the casting. So the casting thing is basically the same as injection molding but for metal. So you can think of it as the same thing. Here the metal, molten metal is poured into these dies. So there are various processes. Sand casting is there, so the core and the cavities are of sand. So, or there are pressure die casting where it is almost similar to injection molding, but it has metal going through it. Then these were the formative processes. So heat and pressure is basically what is driving all this. The second conventional thing is the milling jobs. So or milling jobs means subtractive manufacturing. So you have a block of metal or whatever material you want to make it, and then the material is subtracted from that block to make your final part. So this also has few limitations. You cannot, there are few things, few kind of features that you cannot produce in this. Some internal cavities you cannot make, and this takes a lot of time. It is very time intensive, and the material wastage is too much. You may need only a shell of a box, but you will have to mill the whole solid block, and only the remaining walls will be there, and all the other things will be the waste material which you will have to remove, which takes time and money and wastage. So these were the conventional processes. So now what happens with our 3D, if we compare these to our 3D printing processes, so what will happen? So in traditionally you see high manufacturing costs, like for example in the case of subtractive, and basically shipping costs also, because there are companies which do this thing, and you'll have to go there, and some kind of supply chain and logistics, the delay in logistics and all is required. But in 3D printing it is reduced if you plan it correctly. In prototyping, for example, if you have a 3D printer on your desk, you can just design your part today. While leaving from your office, you can you can start the print on your 3D printer, and in the morning when you will come back, you will see that the part is printed. So you have designed the part yesterday, and today in the morning you have the part in your hand. So nothing can be as fast as that, even because the other processes, you cannot go for the formative process. You cannot make a design today and go to this mold thing. This mold, manufacturing a mold takes weeks, and same goes with the casting thing. You can do it fastly in the subtractive mode, like, but these machines are very heavy and very costly, and you can spend a lot of money on that as compared to the 3D printer, which the part will not cost you as much as that, and it will be very fast. So similarly, okay, so the next point is less innovative design due to machine constraints. Okay, so as I said, in traditional design, there are few limitations in the way you can design the part, which means there are some features like you have to take care of how thin walls, how thin your walls can be. There will not be an undercut. Undercut is, let's suppose, okay, so I'll tell you about the undercut. I cannot explain you in this image. So undercut is not possible in these kind of things, not even in the subtractive, but you can make undercuts in the 3D printing thing, and it will have sharp edges. There will be you cannot have sharp internal edges on subtractive because there is some radius to the tool, the drilling tool or the milling tool. So it will result in a internal radiuses of some, even if you are using a one drill bit, it will again have, and you're making a cavity like this, so you'll have a half radius of this edge. Okay, so but in 3D printing it's not like that. You can have that, so that is not a problem. Then ready for your market is reduced significantly if you have your 3D printer. So basically these are the cost, the design freedom that you get with 3D printing. Almost any kind of design is possible with 3D printing. Okay, then the speed. So no other manufacturing process from your design finalization and your first part production is as fast as 3D printing. Okay, so we'll go to the next thing. So why we need 3D printing? So it is basically retrospective of what I just said. So to reduce the development time, so the time taken for your product to go to market reduces very significantly. Then again, you reduce costly mistakes. Like I said, in the case of the injection molding, if you make some mistake in the design, you'll have to make the whole injection mold again, which will take weeks, which will cost lakhs of rupees, and it's not a very good way to make things. So, but in 3D printing, if you make a decision wrong or you have done any mistake, you can change it very fast. Okay, so the next is data-driven technology. So the the traditional processes, you know, have many disadvantages in terms of data-driven approach, because in this you just have a 3D file, just like a normal 3D. You don't have to have too much knowledge about the specifics and how the CNC is working and all those things. You just have to make the part. There are some parameters that you have to change, but there are not too much, and it's very less technical to 3D print a part than to, like, if I am a designer and I have to do the same thing, then the CNC, the formative and the subtractive is a new industry itself. But in 3D printing, you yourself can make the parts in your 3D printer. It will not take you you don't have to be too technical to understand these things. Okay, so no extra investment to produce jigs and fixtures. Yeah, so let's suppose you are making an assembly of, let's suppose, 5 parts. So but you cannot make it in a single part due to the constraints of manufacturing in the subtractive. Let's suppose you have to make a cavity, so you will have to make 2 parts which will enclose that cavity, and you will have to make those 2 parts differently in the subtractive process, and then you will have to assemble them as an assembly. So but in 3D printing you can make those parts as a single part. So So jigs and fixtures are used basically to align those assemblies and all together. So, but in 3D printing, if it is being printed in a single part, you don't need any process to fix it and any supporting tools like jigs and fixtures to do the same process. So, so one example is the rocket engines. Nowadays, some companies are making the rocket engine, which is a very complex and have has too many pipes and all those things. So earlier it was made by conventional, so it had to be done in so it had multiple parts, like it has 50 parts or something, uh, like critical parts. So, but with 3D printing, we have reduced it down to like the main chamber and the incoming and outgoing things, and all those things are now a single part. So this is an example for that. Then the material wastage is nearly zero, which means like in subtractive process, you have to remove the material from the block, so it becomes wasted. So if compared with the subtractive process, the material is very less wasted because we are adding material wherever required. We are not removing any material. So adding material means we can only put the material where it is required. So the wastage is automatically very less. It is not zero, but at some point there it is zero, but it depends on the part. So it's a subjective thing. Okay, so again, no design limitations like conventional machining. There, the part that you're seeing in this video will be very difficult or almost impossible to make in a subtractive process, but you can make this in a 3D printer as an assembly. You can even print assemblies in the 3D printer as one part. So like you're seeing these three, four gears and the gear housing and all the structures that you are seeing below this can be made in a 3D printer as a assembly, and you just have to remove that from your build plate, and you if you rotate one gear, the assembly will start working. So this is what the possibility that you can make. Okay, so what is the workflow of the 3D printing? So first of all, we have a 3D CAD file. Just like we have an image for 2D printing, we have a 3D image for the 3D printing. So we basically convert the CAD file. CAD file is a vector format. So we change it into an STL file. It's just a file format. So we export it as a STL file. Then then to be able to print it, we have to open a software which will convert the design, the STL file, to a format which is readable by the printer. So that slicing software or the intermediary software depends on what technology we are using, and there are multiple parameters that you can set, like what will be the quality of the print, how fast or how slow the print would be, and wherever the supports are required or not. So I'll talk about the supports in future slides. So this is basically an intermediary uh, software which converts the STL to a machine readable format. Okay, so this is similar to CAM software like that you have in your 3D print, that your CNC machining thing. So you have your CAD file, you put that in your CAM software. So and then it exports the G code for your CNC machine. Similarly, it gets this STL file and outputs the G code for your 3D printer. So G code is for one kind of 3D printer. There are other 3D printers also. So the output format depends on what printer we will be using. from that process. So then it is converted into the G code file. The next step will be to insert that thing into your 3D printer and start the print. Then it will start printing it, and that process is the additive manufacturing process. And once that is done, you'll have your physical object in your hand. Okay, so what is the 3D printing ecosystem? So first of all, we need a what is the so in this workflow you can see we have to have a 3D model first. So how do we make that 3D model? We can make that 3D model out of CAD softwares like SolidWorks and AutoCAD and Rhino, all those things. Or if you don't have that, there is another step from where you can get that 3D model. You can scan a physical object with a 3D scanner to make that file for you. So like in the case you're seeing on the top left image, there is a scanner. It's a sense scanner, and it comes for about 50,000 rupees, and you can scan a body or any object from it in fairly decent kind of quality. And then you will have a CAD file similar to the one shown in this first image, and then you can have it 3D printed, and it will look like something like this, like you're seeing in the second image. And this is basically a pre-process for your additive manufacturing, to a new way to get your 3D files. So you will not have to make it yourself. You can just scan it, and there is small level of detailing and correction that you have to do in it, and then you'll have that CAD file in your hand. Then you can do whatever you want on that. Similarly, the 3D printing is an automatic process. So, but there are, to enable kids to be into it and to bring creativity out, you can also it can be used then as an artistic way also. So we have 3D printing pens also. These are filament pens. This is the filament. Filament is the wire of plastic, which is the raw material for the printing process. So in this pen, this wire goes down and starts coming out in a molten way. So right now it's not clearly showing you the right thing. It's a green filament going inside, but the part you are seeing is blue. So, but whatever color goes in comes out. So, and you can make, with your own creativity, you can make parts also. Even if you don't have a CAD file, you can make parts out of it. So this is basically what the meaning and the application of the filament pen is. So, okay, so there are various technologies in the 3D printing. So when we cover this, just let us take a 1 minute break, and we'll come back. Just a 1 minute break. Okay, so let us start again about the types of 3D printers or the technologies basically of 3D printing. So first is the FDM process. FDM stands for fused deposition modeling. It is also called FFF in some printers, just because of the patent and all those things. So FFF is also the same thing. FDM is also the same thing. In this, what happens is your raw material is a wire of solid plastic, and you move that through a nozzle, a heated nozzle, and it comes out in a semi-solid consistency, and it is laid down on a bed layer by layer to make your 3D part. So this is what the FDM machine looks like. So the in below you can see the white and blue materials as a roll of plastic wire. It comes up on this black box kind of thing which has two nozzles. So your printer, your FDM printer can be of one nozzle or two nozzle or multiple nozzles. So let us first think about it as a one nozzle system. So in one nozzle system, your wire will come up. There is a gear kind of thing which can be attached at the bottom also or on the top, which will push or pull the material inside the nozzle. So once the nozzle is heated, it will the material will come out from the nozzle, and this bed that you're seeing the build platform, it will deposit that part on the build platform. So it comes like this. The red thing on the top is your filament. This is your head, and it moves in X and Y directions. In two axes, the head moves, and the bed moves in the Z direction. So for the first layer, the build platform is very close to the nozzle and almost touching the nozzle, and it will lay out one layer. Then on top of that one layer, it will print different layers. So but you can see in the case of this image, we are printing an X. So in X, there are some faces which do not have anything below them. So basically, you cannot make anything in air. You cannot make it stand in the air. So what we do is, just to be able to print those things, we are printing some supports. These vertical lines that you're seeing are the support parts. So you can print those support parts from below with the part, so that when it comes to print this surface, it can be printable on that support. So once the part is completed, you can remove those supports with a cutter, or they are easy to remove. They are not too difficult to remove. They are part of the material. They can be of the same material as in the case of a one nozzle system, or if we have a two nozzle system, we can, or multiple nozzle system. So we can make the support. So you can see this is the support part. So we can make the support out of a different material, so that it is easier to remove. That another material can be water soluble. So you make your part, the supports are printed in water soluble material. The normal part that you require is made in a normal plastic, and you just remove the part, put it in water, and after a few hours, 1 or 2 hours, that support material will get washed away. So you will not have to do any post processing work. So but in the case of one nozzle system, you will have to make these supports out of the same material, so you will have to remove it with some force. So this is basically all which is about the FDM 3D printing technology. So there is two axes, XY axis on which the nozzle goes. There is a Z axis which has the build platform. The nozzle comes close to the bed and prints the first layer. Then the build platform will go down one layer. You can set that layer height in your slicing software, and it will move accordingly. So you can make parts up to 1 mm layer height. So if you're making a 1 mm layer height, if you're printing a 10 mm part, you will have 10 layers. So it will be very thick layers, and you will be able to see each and every layer. But if you reduce the layer height to, let's suppose, half mm, 0.5 mm, you will have 20 layers in the same 10 area, and the layer will be less prominent. You will be able to see less, lesser of that, uh, the thickness will be less. So, and you can go up to 100 micron. So 100 micron is zero point 0.1 mm. You can even go below that, but let us assume zero point 0.1. So in zero point 0.1 you will not be able to see the lines, the differentiating areas between two layers. So then it will become very fine for you to see. So that all can be changed in your slicing software. You can set in the same part, you can, and also it takes twice the amount of time to print. Let's suppose you have 10 layers to print, it will print, let's suppose, in 1 hour. So if you are reducing the layer height by half, so it will take twice the amount of time to print. So you will have to basically optimize between your time and quality that you get. So these are, you can see these layer marks that you are seeing on the X, the horizontal layer marks. So these layer marks will be thicker if you have a thicker layer height, and the part will print faster. But if it is a thinner part, you will not be able to differentiate between two lines, as it will be very close, but it will take very high amount of time to print. Okay, so the second process is the wet polymerization process. And there are two similar technologies which are SLA and DLP. So SLA is stereolithography, the one that I just showed you, which is this one, the second line, which says stereolithography. So what happens in stereolithography and DLP also is that there is, the raw material is a liquid, and it's a special kind of liquid which gets hard, which gets solid, which gets converted into solid once UV light is exposed. Okay, when the liquid is exposed to UV light, the area that is being exposed turns into a solid. So what we can do with this, we have a layer of liquid on the base, on a tank, on the transparent tank. On the base of it, we have that raw material, that liquid raw material, and we put light from below facing upward on that tank, and whatever will be the pattern of the light, the material inside the tank will get solidified. So you can see it better in this thing. So yeah, so this white cutout thing is your tank, and your blue thing is your material, the raw material, the liquid being poured into the tank. And then there is a small permeable window on the, is basically transparent window in the base of the tank, and the projector exposes the light from below, and whatever pattern it shows uh, on the window, the permeable window, that will, that part of the liquid will get solidified. And there is a build platform, so the build platform will be very close to the oxygen permeable window in the first layer, so that it gets attached to the build platform. So whatever material is between the build platform and that window for the first layer, it will get solidified and it will get attached to the build platform. So once that is done, the build platform raises one layer height, and then again the next image is exposed, which gives you the 3D file. As you can see, the green thing is the printed part. So the difference between this SLA and DLP is basically the way the light works. So in SLA, there is not a projector, there is only one laser pointer, and it moves just like the nozzle moves in FDM, the laser pointer moves on this oxygen permeable window in SLA mode. So the point of contact is very less. So it takes some time to fully scan the permeable window area. So, but in the case of a projector, which is the case of DLP, in a projector, what happens? Whole image is projected at once. So the projector thing, the DLP is relatively faster than SLA. So this is the basic difference between SLA and the DLP. SLA has a laser pointer as an image source, which the laser moves in a particular speed and direction to make the shape, but the projector projects the full cross section of that image at once. And then there is an exposure time depending on what material you are using. So if you're using there are different types of UV curable resins. So the raw material is called resin, liquid resin. So some there are various manufacturers for that resin. So some resins take some amount of exposure to get hardened. Some need more light to get hardened. So it depends on the exposure time. So you can set the exposure time on the projector. So or the speed in the laser wala thing. So which means different kind of materials can be printed with the same setup. Same goes with the FDM, where you have different materials like ABS, polycarbonate, and PLA material is there. So all those materials, the difference is in the melting temperature. They have some variation in the melting temperature. So for example, PLA gets molten in 210 to 220 degrees Celsius. The polycarbonate is more than 350. There are other materials also. ABS is 240 degrees. So we can change those parameters in the slicing software so that we will be able to make the part with the material that we want. So okay, so this is what stereolithography is all about. This is also a fairly low speed process as with the FDM. Again, if your layer height is less, you can have a very good detail, but it will take more time. And if the layer height is more, then it will print faster, but the quality will not be too good. Also, the detail that you get in stereolithography is very high. In FDM, you can even if you use a very fine nozzle to print, you can switch nozzles. If you're printing with a 1 mm nozzle, it's just like printing with the permanent marker, which has a very broad tip. So if you are writing with that, you will not get very good details, but you will detailing in very small features and small holes you can make out of these. And but it will take a lot of time to fill the same area that you have filled with the marker. So marker may take one stroke, and you're making a 5 mm by 10 mm line, and if you have to use a 0.5 mm nozzle to do the same thing, then you'll be have to make multiple passes to make the same area. So and but the detail will be high, time will be more, so area will be more. So but in the case of a thicker nozzle, you'll have less time but very less details. Small features will not be able you will not be able to see those surfaces. So but in the case of SLA, since it is based on light, so there is a pointer in the SLA case, but that pointer also is very thin. It is like 50 micron or 100 micron in dia. So which means it is able to make very fine transitions into the features, which means you can go up to 25 micron of features, which means 25 micron is like 1,000 microns makes 1 mm. So 25 microns is very, very less. So the precision, the resolution can go as low as 25 microns in SLA. So this process is used in parts where you need very, very high features, like in jewelry grade details you can get out of it. So the jewelry makers are now using this technology, and the raw material that they are using in this is a UV curable resin, but it acts as a wax once it is printed. So you can make the actual rings and all those things in this, and out of wax UV resin. And once it is done, it is turned into real gold with the injection molding kind of process, which is called investment casting, in which the wax is placed on a silica sand, and it is then heated up so that all the wax is removed and only the cavity remains. Then the gold and whatever precious metal you want to put in, it is put in, and you get your gold ring in a fairly detailed way. You just have to polish it a little bit and cut the extra projections and all those things. And so now you can even make jewelry digitally, basically using this SLA and a very, very exclusive resin, which is a castable resin, wax resin basically. So the next process is selective layer sintering, which was the third one, SLS. So in SLS, the raw material is a powder. So in powder raw material, the advantage is that in the earlier two technologies, in FDM and in SLA, there is there needs to be a support like we have here. There are supports in FDM and in SLA DLP. We cannot make a part without supports in these two technologies. But in SLS, the the unused powder itself is the support for the next layer. So what happens in SLS is that there is a tank of powder which is basically a storage, and then this is our build platform, the one below the elephant, and there is a blue roller on the top, and the roller will deposit one layer full of powder on the build platform. So build platform will go down with each layer, and the tank platform will go up with each layer, and the powder will get transferred with each layer to the the building side from the storage side. And there is a laser on the top, and that laser pointer will put laser energy on the powder, and that is too hot to fuse it. So it get wherever the laser is beamed or exposed, whatever area is exposed to the laser, the area will get solidified. The other powder will remain there. Then the next layer will come, and it will again do the same thing. So even if there is a overhang is a kind of a thing like it is in the x surface which needs support basically. So even if there is a area which needs support here, there will always be unused powder, unsintered powder, loose powder below that surface. So there is no need for supports. Once the part is done, you just have to pick the part from this tank, and you just have to put the compressed air, and everything will get washed off, and you'll be ready with your part. You don't have to do too much post processing or print removal, or you will not have to reorient the part to see if it is feasible, because in these two technologies you will have to also see in which orientation we need to put our part so that we don't get supports either, or we can minimize the supports, or we can only have supports where the surface which will have the supports is not too critical. Because if you put supports, the top area which gets printed on the supports will have some imperfections. So to minimize that, we can reorient the part in some direction so that either we can just go away with the supports, or the supports are minimized, or they are only there where the surface is not very critical. So, but in the case of a powder and SLS thing, it is not required. So what SLS does is there is a layer of powder, and the laser will expose that powder with light, intense light, so that intense light, it will get heated and it will fuse together, get welded together, and one layer will be made. Then the next powder layer will come on top of it, and again the laser will work and it will fuse the same layer, and also it will fuse that layer with the layer below it. So there is a 3D model that you can create basically. So SLS is used for plastic. So because the layer is this thing is very so SLS can be used for plastic and metal, but it is used, the naming is different. In the case of plastic, it is SLS, and in the case of metal, it is DMLS. So direct metal laser sintering is DMLS process for metal, and SLS is for the plastic. But they are basically the same. Only the raw material is different, and the power of the laser. And in the case of metal, it is some kind of inert gas and all is used so that the topmost part, since it is hot, will not get oxidized and all those things. So this is the selective layer sintering. So then this was the SLS. You can see in the last thing, it is the metal one also. So there are three types of metal powder technologies. DMLS is similar to SLS, and only a few application specific differences are there. So okay, so this is that. Then the next one is material jetting. So in material jetting, what happens is you have a material jetting is similar to your normal 2D printing process. Like you have inkjet printers, and in inkjet printers, you get ink droplets out of the ink cartridge, and it will deposit on the paper, and you will have your image. Similarly, in material jetting, uh, the UV curable kind of material is there on the ink cartridges, and it deposits on the bed. It goes through a UV curing pass, and then again the ink cartridge will come, and on top of those previous droplets, it will again put new droplets, and again that UV light will cure it. So with this, you will get your art. So okay, so it is not shown here, but basic idea is like your inkjet printers, material jetting is very similar. Only the kind of ink is different, and you don't have a paper, you have a build platform which goes down one layer at a time. Otherwise, it is exactly same as your 3D your normal 2D printer, inkjet printers. Okay, then the next one is binder jetting. So binder jetting is a powder based material. Okay, like in the case of the SLS, we have a powder base, powder raw material. Same goes with your binder jetting, and you don't have a laser on top a headlight or whatever it is they are developing, they will make it in a 3D printed form first of all and validate the design, and then only they will go to the production and all those things, or even planning for production. So that is there. Then defense, in defense, because the numbers are very low, production numbers, and a very exclusive part has to be made, and or complex part you can say has to be made. Hence also there are possibilities for the metal 3D printing. Somewhere it can be soft tissue, hard tissue in your CT scan, and you can selectively export the 3D files for your like hard bones, soft bones, which are cartilages, and soft tissue, all those, and who make things exclusively for some people to high-end people. Though those are using these things. So jewelry is a part of a fashion thing. So in jewelry, it is very highly used. Also for movie props, 3D printing is basically what we're trying to say. Okay, so what about the global growth rate? So the actual booming growth that the 3D printing saw was from 2012 or 13, and from then it has been exponential. Earlier it was only meant to be used by high-end companies, and only high-end companies were making the 3D printers like Stratasys, 3D Systems, and some other. But now even you can make your own small 3D printer in your home. It most technologies are open source now. You can make your 3D printer at home. You can experiment with all those things and whatever you can do. So, but the growth is in India and the neighboring places, the growth is very high, because we used to be very far behind in using traditional uh, technologies. We were using traditional technologies, and not even now some dyes are made with wood right now, with and are hand carved in India. We have some places which have that too. So but now the time is changing, and people are getting into these things. And since also it is an affordable technology, basically FDM1 is the most affordable thing that you can get. So you can get a 3D printer as low as 20,000 rupees or even lower for an FDM machine, and if you make it yourself it will be even cheaper. So which means it is more accessible to low margin areas. So which will help in the growth of the industry and also other industries. So very much too many industries are there which will need 3D print. They don't know it, but their job will be easier if they use 3D printing. So the more exposure they get, they'll be better be able to understand. So basically the growth in our country is very high. So and there's a lot of potential there. So that is that. So okay, so what is the basic contribution, and to just show how much what industry is using what and all. So in dental industry, a lot of 3D printing is being used. Extensively it is being used, and in automobile it is also, again I said, everything goes from the that same process of prototyping with 3D printing. So that is there. In aerospace we have the design we need design freedom to optimize our parts. So that can only come from 3D printing. Then again industrial machines, and which comes into jigs and fixtures and all those things too. There also the need is very high. Consumer products, every consumer product is a physical part, so whatever goes into it has to go from the development process of iterations and prototypes. So there also 3D printing is used, and academics also to do research and to come up with new ideas. This is the best tool to physically to turn your idea into a physical thing. So, and there is a lot of scope due to this in research areas. So that also has a major part in the 3D printing world. Then there are some other like architecture. There is very less usage in architecture because you will just need a scale model and all. Though now there are some companies which are building actual homes out of 3D printed concrete. So concrete or some kind of mortar is used and is placed as an basically it is like an FDM process, but a very large machine, the large nozzle and special material. So they are now building homes using. There are some companies only, not too many, but they are doing it. So and again in military, like I said, in defense there is some scope in that. So and some other places where it is required. So this is what it is. So again, as an example, building block houses. So as I said, there are some companies which are building some small. It's not the right image to show, but basically they are using very large FDM machines which extrudes paste. So that paste is a mortar and it is laid down layer by layer in a very good kind of shape so that the full house is made, and they're able to make like 2 to 3 200 feet 200 square feet houses in 24 hours. So it's very fast as compared to manual labor because it cannot be automated, but we can basically now automate the building process part using this 3D printing thing. So yeah, and then you can see in footwear industry also it is basically a consumer product. So prototyping and all those things are very important. But for high-end customers like athletes and all those niche parts, the design of the footwear and all those things can be optimized if they are thought of to be manufactured using the same 3D printing also. So by not, so we can produce the parts with conventionally, but to better optimize it for very in a customized way for the athletes and all those things which need very customized things for themselves. So we can use 3D printing to serve them with what they need. Then there are very small amount of projects where even the full car is being 3D printed, the whole structure basically, not the parts, not the dashboard and all those things, but the actual structural member is your 3D printed part. So then in optics also there are some kind of shapes which are not possible or takes too much subtractive process to make in optical industry and lenses and all those things, but it is a very high end use case scenario. So optics is also 3D printed nowadays. The machines are very costly, but they do make it. And there is a possibility to even make human organs in the future. Some people have tried it. They have not actual organs, but like tissues and skin tissues and all those things in Pretty Dish. They have printed that, and so the ultimate thing will be if we have an organ that is 3D printed in our body. So it's not yet possible, but it will be in the near future. So also it's a very good use in space station and all those areas where you cannot take every single spare part out in space because of the weight considerations and space considerations. You just have to have a 3D printer, and whatever tool or spare part you require, you can just make it there in space. So similar thing goes with the food printing industry. Nowadays, some food printers are also there, which you can customize and make very uh, basically personalized food items and all those things. Also, you can use the food 3D printing with automating some of the food manufacturing process. So okay, so this is basically telling us how much of the percentage of workforce is skilled in India. So as we can see, it is very less as compared to other countries. So 3D printing is a skill which is not very difficult to get, and there is a lot of since there is a lot of scope there also. So we think that people should come into it. It will also benefit other industries and all those things. So this is what we feel. So there are other things about 3D printing, like where do you need to have from where do you get the model? Is it going to be a modeling grade or an engineering grade model? And also the design complexity. What all can you manufacture with your 3D printer? With which technology of 3D printer? What is possible? What is not possible? Where what are the design limitations and strengths of the 3D printing? All those things. So these things can be learned online. You can see other places also. Since it is a long time now, we are almost 1.5 hours into the session, so we'll not do too much. And but I think we have covered all the basics of the 3D printing, and so we will wrap up shortly. We will not have too much of this now. We'll now get on to the uh, okay. So this was made for the questions, but I think now we are uh, streaming on YouTube. So I don't know if I can get some questions. Okay. Yes. Yes. So you can imagine if you are making a cube. Okay, if you're trying to print a cube, so the first layer you will see only a square shape. The first layer will be a laser pointer will first of all go to the boundaries of that square, and will scan that area, and then it will fill in the inside area. Okay, so the whole square thing will be fused together on the first layer basically. Then the next layer, the loose powder will come and cover the whole area of the bed, and consequently also covering the square that we earlier made. And again the laser will come, and on the same area it will again do the scanning thing. So the layer will get fused together with the layer below it, and also all the particles will get fused together to the same layer. So this layer number 1 and 2 are now one single object, and the rest is the loose powder. So I think uh, this is what he's looking for. So I think I have answered this, and there is nothing to it else than this. So we can now, I can, okay. Okay, thank you so much, sir. And we hope that you have understood something from this session. There is because I don't know how informative I was. So we'll be waiting for your feedback for the same. Yes, Okay, sir. So thank you everybody. We are now finishing it. So okay.